Good afternoon. So today we continue from where we left off for the JPEG compression, right? Do you have any questions about what we covered so far, especially in the JPEG stuff? So the high-level stuff we had was, you take an image, you convert that into from RGB to YCU, CBCR, or YUV, or one of the color spaces where we know that we see differently, right? Like brightness and color, and then we scaled them differently, right? So we took the image, split them into 3 components, so we can drop certain frequencies, right? So we drop the color stuff, and then for each of those, we convert them from the spatial domain to a spatial frequency domain using the DCT mechanism. The idea here is, in that space, we can drop the high frequency or the details. The observations where we don't see color very well, and we don't see detail very well, right? So we did the conversion. So the next step in the process is the quantization process, which essentially is the process of dropping the components, right? So when we convert it from the spatial to the frequency domain, you have a long set of bits, and we want to make them as much as possible into 0, because that means you're reducing the number of symbols. And the fewer symbols you have, the longer runs of things you have, the more compression you can achieve, right? And we want to make this such that, so the real magic happens in the quantization table, right? So if it drops components that you cannot see well, then you'll be happy, right? And so the way you do that is you take the table from you took the image, took 8 by 8 blocks of the image, converted each one of them into frequency domain using the DCT, and that's the FUV matrix. So for each one of those, you divide them by the quantization table, right? And that gives you the quantized values, which you can compress it in normal fashion, right? The magic part of JPEG is this quantization table depends on, they do a lot of studies to figure out what sort of table looks good for people right? So they do a lot of studies based on the kind of images that they're designed for, the kind of monitors that people are looking at, and the kind of stuff that you do, right? So most of the international standard bodies happen to be in Europe. So they essentially do a study on, for given technology, for a given monitor, what kind of stuff you would notice. So they come up with this matrix. It's kind of formatted differently. You don't have to remember them. It's a default table that JPEG library comes up with. For the luminance, you have certain number of values, and the chrominance, you have certain number of values. So you choose different set of values for the different ones, right? The standard does not say anything about what kind of a table you should use, but you have to use some table which will let you get good compression, right? And you're free to use a compression table which is all ones, right? What would happen if you choose a table which is all ones, or all the same? The idea here is you're trying to drop different frequencies differently, right? So remember, we are doing the rounding division, right? So if you want to drop more of the high frequency components are the ones over here. And remember the DC component was here. The frequency of the components is going down as we go this way, right? The highest frequency was here, right? So if you had an equal number, if you had like 1 for all of them, that means you're going to drop all the frequencies equally, right? Remember the equation. You divide by the corresponding entry, and then you round it. So if you had it all equal, then you would drop all the frequencies equally, which essentially defeats the whole purpose of doing all the stuff, because we want to be smart about what we drop, right? So you will notice that the values over here tend to be larger than values over here, because since you're dividing the stuff, larger values means that you're going to likely make them to go to 0, because this is rounding integer math. So whatever number you have, so for example, if you had a value of 99 here, right, then once you divide by 99, you get 1, right? Anything less than that, you make it 0, right? Whereas over here, you tend to leave a lot more of the stuff, right? And there's also different tables for the different stuff. In general, the pattern is over here, you tend to lose more. And the luminance is a little bit more complex than here, because here you notice most of them are practically 99, which means that they're probably trying to get rid of almost all this components, because it's in the color domain. But on the luminous domain, you see different variants. You still see 103, but like this one is 64 and so on, right? And you don't have to remember this stuff because it's just one table which seems to work very well. And for example, if you have Adobe or something, then you would, if you come up with a better matrix which make the image look good, then it's something that you're going to keep. You're not going to tell your competitors or whatever, right? And when you set the quality factor in like standard or fine or what have you, you scale this matrix, right? If you make if you scale the matrix sufficiently, then you'll tend to drop more components. So changing the quality factor essentially means you scale this matrix up and down, or you can use different matrices for different compression, right? So none of these standards define what they should do, and this is one thing that you'll see when you go to MPEG and stuff. Because a lot of commercial interest involved with this stuff, the standards don't specifically say how you should do it. It's more driven towards making sure that any JPEG image can be seen by anybody else, not on how they should look for the same kind of image. So if you take a raw image, the standards would say, if you make it into a JPEG, any JPEG decoder should be able to read it, but not how exactly you should compress it, right? So you are free to choose your own quantization table here, and as you'll see for the MPEG and stuff, you're free to choose your own compression, and depending on how much you want to invest in this, you get different values, right? So we can go through a little example to see how these things work. Again, you don't have to remember the numbers, but just see the general concept, right? So we take that particular image, and the little black square is the block that they're looking at, right? So the raw values for that particular entry is this one, right? It's a bunch of grayscale values. So once you do the DCT, right, you get this, right? You don't have to remember what those are, but essentially it changes from this one to this one, right? You may already notice that the highest value is the low frequency components. The high frequency tends to be smaller, right? But that just happens to be because it's a photograph. So then we take so we did the quantization, right? So in this case, we did applied the quantization matrix, divided the values, and as you'll see that since the DC component was pretty high, 515, that still survives as 32. Most of the other components became 0, right? So in fact, most of the JPEG, most of the time, most of the high frequency, you would lose it. And if you look at it, there's about 7 values which are non-zero. Everything else is 0, right? So in that particular block, we dropped of the 64 entries, only 7 have some value. Everything else is dropped, right? And we will use this for compression. We'll use this for compressing using Huffman coding or what have you. And one of the things to remember is all those things, the fewer the symbols you have, the more compression you have. And the more runs of things you have, the better compression you get. So in this case, there's only 7 symbols. So not 7 symbols. There's only 3 symbols, -1 and 6 and 32. And you see this long, actually there's 0 too. Then you see this long run of 0, right? So that means it will compress very well, right? The reverse process is you take that image, you apply the inverse quantization matrix to get the value back. You do a reverse DCT, and you get this value back, right? So this matrix gives the difference between this and this. This is the original matrix. We did a DCT. We did a quantization, and then we dequantized IDCT, inverse DCT. You get these values back. So this is the difference between what the original was and what the current one is. So this is the information that is lost, right? And if you do it right, even though it looks like you lost a whole bunch of information, you should notice a difference. Does that make sense? So since since one of the things we showed in last class was the frequency components was going certain way, the way to unravel this matrix in the spatial domain is through a zigzag pattern. So essentially, you read from here, you go down like this, and this gives you the pattern from the lowest to highest frequency. So you do a zigzag way of reading the matrix, right? Again, this has implications. We don't really worry about this in particular because we're going to look at video as a more challenging example. But if you take courses in operating systems and all, one of the things is you want to look at locality, right? You figure out how the matrices are laid out, how the memory is aligned, and all those things. And so you had a matrix, right? You had a fairly big matrix. So if you had a 1,000 by 1,000 image, you have a 1,000 by 1,000 image of certain depth, right? You sometimes go through it row-wise, sometimes go through it column-wise, and sometimes you go through this weird zigzag pattern, which is good for you in your programming sense, but it does it does bad things for your locality, right? Remember from your operating system, you worry about locality. Now you're going through in a weird fashion. It doesn't fit into any architecture. It doesn't fit whether you're going row-wise or column-wise. Now you're sort of looking like you're going in a random fashion. It probably doesn't matter for you if you have a small image, but large image, you tend to mess up all your caching and stuff, right? And there are some operations you can continue to do in this domain, in this spatial domain, right? Sorry, in the frequency domain, in the quantized stuff. There are some stuff you would have to uncompress and do it again, all over again, right? So can you think of one operation that you can do in the frequency domain that you don't have to? So JPEG process, you take the image, you do a DCT, you do a quantization, right? That's what you store. That's what you compress, right? So what kind of operation do you think you can operate directly on this domain? There are certain operations where if you want to do it, you would have to go through all the process, get the original image back, do a certain operation, and then store it back, right? And every time you do this, you lose quality. Every time you take a JPEG image, compress it again, uncompress and compress again, you lose quality. So if you do this, if you take a JPEG, right, and you want to do some operation on it to get another JPEG, right? Right? The way you would do that is you would do decompress and do this operation. This is a simple way of doing this stuff, right? So going this way, that means every time you do these two processes, your quality goes down. So if you have a picture collection, and if you're trying to do this every time, then it gets messed up, right? So for example, if you take this image and you want to add time, let's say you want to add time into it for whatever reason. I mean, you have your software which does this stuff, right? So if you want to do this, do you have to go through this process, or can you do something smart? I just added the time over here, right? Yeah?
Well, it would be nice if we could just append some characters on your file that says put the time here, but I don't know if JPEG supports that.
No. Yeah, so you sort of like an alpha channel or something, right? Like extra channel to say add this on top of the image kind of thing. That's an alpha channel, right? JPEG does not let you do alpha channels, but let's ignore alpha channels, right? If you don't have alpha channels, JPEG does not let you create these macro operations on top of the image, because JPEG decoder has to decode the image. It does not know about operations you can do on the stuff, right? So to give you a hint, if your compressor is smart enough, right? Remember you operate on 8x8 blocks, right? So you realize that so essentially when you think of a JPEG image, you're not operating on a JPEG image. You're operating on this 8x8 blocks, right? So your program may be smart enough to notice that all it's being changed is this, right? So it can take those blocks, decompress them, right? A little bit trick because you're still doing the Huffman for the coding for the whole image, and get this component, do whatever operation you have to do, right? Again, convert that to frequency domain. You had the original one and then this one, then you can store it back, right? So this is where this is why you pay more money for certain software or other software, right? So some of you may so if you buy like software like Photoshop and all, they tend to be much more expensive than like your little apps you come with the Windows or Mac or something, right? Because the more expensive apps tend to do something smarter like that, which tends to retain some of the quality of the image as much as possible. Whereas another operation, if you want to make the color a little bit redder, if you want to change the whole thing redder or brighter, if you want to do something on the whole image, right? If you want to make it, certain applications have an operation called enhance, which makes the whole image look different, better, what have you. Those would have to uncompress the whole thing, so you lose quality, right? For the most part, you may not notice it, but if you do it enough times, you notice it because you lose these things all the time. Even if you take the image and then you compress it again, you lose this factor, right? So don't do that. I mean, don't manipulate on JPEG because it's not designed for compressing back and forth. It's designed to be kept in a certain image, right? So the other thing we notice is in that example, the 32 is kind of sticking out. 32 is sort of like big and it's kind of sticking out. Turns out the DC component is the average color of the image, right? So it tends to be fairly large. So if you make a Huffman coding of the whole thing, you have the 32 kind of sticking out, and then you have the other symbols, which all tend to be small. In general, that's true. In general, the DC component tends to be much larger than the other components. The DC component, which is the average color, tends to be similar across the different blocks, right? So if you think of this image as sort of like the sky, the average color of all these will probably be bluish, will probably be similar. Let's say 32 is blue, right? So you have this 32 and a whole bunch of small numbers, and then you have like say 33 and a small bunch of small numbers and stuff. So one way to get more compression is we separate out this component and this component and this component, and they compress the DC component, which is the average color, using a differential coding. So essentially, for example, if the image had those numbers, right, 150, 155, 149, 52, what have you. If you're doing a differential coding, you would store 150, and then the difference, if your predictor was the previous value, so you would find out 5 minus 6 and so on and so forth. So that way you compress better those components, right? So this is another way of getting more compression out of this thing, because we observe that most of these things most of the things in the middle, most of the metrics here tend to go to 0, but this one will always be there because that's the average value, and using a separate coding value for you helps. Is that clear? So we're using the techniques that we know, and especially using the fact that these images are written that way, right? So all this have implications of how you decompress the image. When you decompress the image, it's no longer, you're not dealing with, let's say you have a 1024 by 1024 image, right? You may assume that it's a 24-bit color image, but when you're operating on the stuff, you first create three matrices. Few of them are 1/4 of this image, right? The color ones tend to be 1/4 of this image, and then you're doing operations on this which mess with all your locality stuff, because you're doing the zigzag stuff. You are taking some component within this matrix. You take these components and then add them into a certain way, and then you do certain other components. And when you compress them and decompress them, right? If you use the separate compressor decompressor, when you're getting the image back, you fill these values separately. You fill the corner values separately, and then you get the other values through the Huffman, and then you do the cosine and stuff. So you go through lots of these operations which are very bad for your locality, right? And for the most part, modern machines are fast enough that you don't notice a big hit with those because the images that you operate on tend to be something that you can deal with, right? You can still notice it somewhat if you have a very large image, right? If you have like a 2000 by 3000 or some large image, then you notice that even your fastest machine would come to its knees, right? What's the biggest image you dealt with? I guess the most cameras, commercial ones, tend to go to like 10 or 12 megapixel, right? Have people dealt with like 12 megapixel kind of stuff? Yeah.
I knew a guy once who was obsessed with sending me like 40 megabyte TIFFs.
Okay.
And they were really big dimensions.
Okay. So yeah, TIFF is a kind of a weird, I think I mentioned it in one lecture, right? TIFF is the file format, right? Same as when you say JPEG, it's really JFIF, right? JPEG file interchange format, right? So JPEG is a compression. So you can have a TIFF with the JPEG compressed image, or you can use TIFF with the lossless compression image, right? Because that's the file format on top of this stuff, right? So if you have 40 megabyte, and if it's really good quality image, then you tend to, I mean, most machines I know struggle really hard with that, right? Even 10, 12 megapixel, it struggles because you not only need a lot of memory, right? Because when you talk about, let's say 4000 by, like 12 megapixel, like sort of like this, right? You have a big matrix, which is hard to deal with because it takes a lot of memory, but you're processing it and going through with it in all this weird fashion that you lose. I mean, all kind of your locality in terms of caching and all those things are out the door. So hopefully, if you pay, you expect like Photoshop or something to be smarter about this and rewrite the code to be more friendly with the architecture rather than friendly towards the algorithm, right? In the algorithm we split all the stuff and we're doing these things, but in terms of the machine that you're operating on, you would want to make them nicer, right? So if they're so hard, how come your camera has no trouble dealing with these? When you take a picture on your camera, right? If you have like this high megapixel camera, it takes some time mostly to write the thing into your memory card, right? Not that much into taking a picture, right? Yeah.
Is it specialized hardware?
Yeah, they use hardware to deal with this stuff, right? And one of the things you notice is they build the hardware to do this stuff because otherwise there's no way you can do this on this little things, right? So that takes it to yet another level of how to build this hardware. These are very specialized. You can think of them as specialized supercomputers doing certain kind of things, and it's good. I mean, the hardware can let it do some things. It can't do other things, and it'll become more clear when we go to MPEG or video sense, where we want to make it as smart as possible to get as much compression as possible. We have to use the hardware because otherwise, you'll notice it'll take a long time to operate on those things. But you don't get as much as you can do if you have complete software, right? And there's a lot of desire. So the JPEG does support 4 different modes of operation, right? And only the top 2 are popular, right? The lossless mode we discussed earlier is definitely not popular because you get horrendous compression, right? So you may, for example, use that within TIFF. So you may use a TIFF image with the lossless JPEG as the compression for a lossless image. For most practical purposes, you don't use the lossless one. Progressive mode is used because if you have an image like what Sean pointed out, if you have a really large image, right? You don't want to have to wait for the whole image to come to you. So you would like something where things, as you get the data, you're able to display them, right? And this actually came from GIF days because GIF used to support this kind of a mode. So the idea here is, let's take this example. You have a 40 megabyte file, right? And you are downloading it, right? So if you're downloading it for saving, you don't really care how it happens to you, but you want to show it on your browser, right? let's say this is what you want to display. So what I would really like is if you send me 10% of this image, I would like to see 10% of the output, right? So it may, so that's the goal. So I want to see 10% of the image. So in the sequential mode, how do you think, what can I do to, if I get 10% of the image, how would I be able to show that? Suppose the way I store the image is I split them into macro blocks, right? And let's say I store them all as sequential. So let's say 1, 2, 3. So I'm storing them as 1, 2, 3 macro block kind of stuff, right? Ignoring the difference between the DC and the AC component and stuff. How would 10% of the image show up on your screen, roughly speaking? Yeah.
Just be like the top straight.
Yeah, so you would sort of get like something like this, right? You would, if you're doing this, roughly speaking, this is what you sort of get, right? So you get 10% of the data, you get 10% of the image, right? For many users, it's not enough because this is kind of, it doesn't give you enough information, right? So if you look at photographs, this tend to be like, for example, the sky. So you get the sky for a while. So especially if you're in dial-up or something, you would want something better. So what you would like is you would want this whole image. Ideally, we would want the whole image to be here at 10% quality, right? And that's the goal of the progressive mode. The progressive mode is I want the whole image, but I don't want it need not have all the detail, right? So if you looked at the progressive formatted JPEG, you may have noticed it. You may have seen this when you go to web pages where you have this sort of like this image and then it gets clearer, right? How many of you noticed that kind of image? So when you notice this image, what is the first level you see? Like, do you remember how it kind of progresses, how it kind of goes forward? Yeah.
Just starts out looking really pixelated and gradually gets sharper.
Yeah. So if you look at, I'll try to find an example image, like really a long image, and put it on the thing. So it looks sort of pixelated. Or if you look very closely, you'd see all the DC components first, right? Meaning you will see the average colors over here in a sort of like a fuzzy fashion, and then it'll start to become clearer, right? It'll look like it's coming into focus, right? And essentially so you get the lower frequency components and you get the higher frequency components and stuff, right? The challenge is you have to do something about it. It's not a trivial task, because if you just take the image, and if you just take the low frequency components and then try to send them, and then the next frequency components, right? What would happen? I'm doing a naive progressive way where we have the 8x8 matrix in the frequency domain, right? I want to first send the low frequency components first, so I'm going to send this, right? And then I'm going to do the next low frequency components. So let's say I send this first, and then say I send this second, I send this third, and I send this fourth, right? What would happen? It's going to be wrong because I'm calling it naive, right? So if I try to do this, what do you think will happen? Think about the whole notion of JPEG, right? We try to drop certain components, right? What is the component that we want to keep, right? The more we keep of them, the more information we have, the more data there is. The ones that we drop more tends to be zeros, right? If I try to do something like this, right? If I try to do it like this way, right? There's more information here, right? So in terms of in the frequency, if you look at the amount of data that's to be sent, right? There's more data to be sent here as compared to here, right? If I do it like this, let's say all of this tend to be 0, right? So even though it looks like I'm sending a lot of data, once you compress it, it's all 0. So I can send, if I use a simple compression, I can say I'm going to send 32 zeros, right? So there is less information here even though they are the higher frequency components, there is more information here, so they don't compress as well, right? So if I don't do it right, it will take you, let's say, roughly speaking, 80% to send all the DC components for the whole image. And then the high frequency components, let's say, is just the 20% of the data, right? Because that, does it make sense? We took great care to make sure that we split them in a certain fashion. So if I don't do something different, if I just send it the way we were doing it, this one has lots of zeros that we see on the screen, but this one is also more zeros. That means when you compress them, the more repetition you have, the better compression you have. So this one doesn't have as much data. So when I talk about 10% of the data, if I only send 10% of the data, all I would be able to send is, like, say, 5% of the DC components. So you don't get what you want, right? So that is important. So you have to do something different. And this comes back to us in terms of when we do the MPEG and stuff, right? MPEG, one of the reason why we do all this stuff is we want to understand that when we do certain operations, you want certain things, but you have to be careful on how you get, right? If I just send 10% of the data in a regular JPEG file, if I take it into frequency components, then you don't get any savings at all, because we took great care to make sure certain things happen a certain way, and you don't gain anything. So, sorry. Sorry, I've got it. So we have to do something separate about those, right? So the way they defined it is, again, you do an analysis. In the progressive model, they use the spectral frequency to figure out which of those things are sent first. So in the scan 1, they send DC and AC1 and AC2. The scan 2, they send AC4 and AC3 to AC5. So as you move on, you get more of the components, right? You get more of the frequency lines. The other thing is, you don't now transmit them. You don't actually transmit them as they are. You do the different frequencies, right? So the idea here is, sorry. So if I have like 155 and 200 for the DC components, I split them into bits, right? So if I split them into bits, if I look at the certain bits, right, they'll tend to be similar. So I get good compression. So I split them into different frequency bands, and then I split them into these bit values. So progressive compression gets good compression, not as much as what you get for the base stuff. You have to do these kind of tricks because the way these things are set up. If our goal is 10% data should show 10% of the whole screen, then I have to do something like this, right? Which also means that the coding and the decoding is different. Though they do the DCTs and stuff, the way they proceed to the next step is different. That means the coding complexity and all becomes, your code becomes more complex, right? Does that make sense? So all this is trying to build up to the real deal, which is the video, right? Most of our computers that you have, even though it's sort of annoying when you have like a big image, if you have a 12 megapixel image, if you use your normal machine like laptop or something, if you do operations on it, if you want to move the image and stuff, it'll sort of kill your machine, but it's still okay. It'll probably take a half a minute to do stuff. The real deal is when you go into video, right? So the video, the nice thing is that it has lots of data, right? And we want to operate in video. That's one of the reasons why we are interested in this whole thing. So video, in a simple sense, consists of number of frames, right? We talked about before. So we have certain number of images. So we can do all the stuff we have learned so far, which is when you have So let's think of your video object as a set of images, right? So you have a set of images, and you're still going to have redundancy within a single image, and let's call it spatial, right? So you have redundancy within a single image. So we can use a JPEG like we talked about to get compression within a single image. So we can, let's say we can do JPEG style, right? But the difference between these two images would be small, right? Because if you're taking natural phenomena, if you're taking stuff like people moving and stuff, the difference is not going to be that much because people don't move that fast, right? The motion is not too high, and the rate at which we're capturing is also high. So if you're capturing 30 per second, so if I move like this, right, within one of those frames and the next frame, I might have moved like only slightly, right? So when you look at that as an image, the amount of information that is changing between these two are smaller. So what I want to use is some sort of mechanism that we looked at to get compression on the single image, and some sort of diffing mechanism to get the next scene, right? So that's the stuff that we can do from what we've done so far. You sort of applying the sound kind of model. I can find out that the difference between these two are small, so I can tend to use that, right? Turns out we can do a lot better than that, because turns out between the two frames, even though things don't change all that much, they change enough in a subtle way that the pure diffing messes it up, right? The point is, when cameras operate on people, there are a couple of operations they do, right? One is called panning, right? So I may move the camera this way. So between these two, I may have an image where I sort of look like I kind of translated a little bit, right? So the image may look different, but they're not really that different, right? And people may zoom into an image and zoom out. So the image, the objects tend to get bigger, right? And the other factor is the movement is usually restricted, right? So in this particular case, the camera is videotaping me, right? So it can actually see this whole board, right? Between the two scenes, the only thing which is moving is me, and once in a while the slide, right? So if I want to do a diff, I don't have to do it. If I do a diff of all the things of all this image, I get a sort of average kind of behavior. If I can kind of isolate me to this component and only do a diff here and this, if I separate them out, I can get better. So the key here is we are trying to figure out. We are trying to figure out what's the difference between these two images, right? That's the main thing with the video thing. So we know how to deal with a single image. We know how to deal with the differencing, but we want to make it more video aware, right? We want to be able to sort of not only find the differences, but also do other operations based on what people tend to do. And if I combine both these stuff, then I get good compression, right? I know how to deal with this. I know how to deal with this thing. Then I get good compression. And for the next few lectures, we'll look at MPEG-1, MPEG-2, MPEG-4, and all those things. And they get progressively complex in terms of how far they can look to see what is happening, right? So, and the simple way of looking at this is called motion vector, right? So the idea here is if one frame and the next frame, you have an object here, let's say a ball, and you have an object here, right? We want to figure out how much it moved. We want to figure out what's the translation. So then we can say, in the previous frame you had this ball. In the new frame, it would have been moved a little bit over. So we want to send those things. So we are doing analysis of the image to figure out what's happening, right? So I saw some good examples in this particular website. So in this case, there's some image of this stuff, right? You have to, do you see? It's sort of, they were panning, right? They moving the camera. So between frame 1 and frame 2, things sort of moved, right? Can you see it? It sort of moved a little bit, right? So if I just do a diff, I see a big motion, big noise, because essentially what happened was this thing was here, and then the next one it moved, right? So I see that there's all that big movement, right? So the diff image, even though you are on the right track in terms of the difference between these two images are not that big, they're moved in certain fashion, so that when you look at it as raw data, you have enough information here, right, the delta, that you don't get good compression. But if you're kind of smart, if you knew that there's a translation, so if I take the original image, shift it, and then do the diff, right? So so I take this original image, right? Basically, I'm saying on the other end, just shift this frame and then see if there's any difference. And the amount of data is very little, right? And so that's the notion of the motion vector. I want to send, so I get better compression by doing this processing, this kind of stuff, right? And so different algorithms do different MPEG-1, all those things use different complexity. And so if you think about compression, MPEG-1 is far simpler than MPEG-2, is far simpler than MPEG-4, and so on and so forth, right? The other key thing here is all these operations are essentially image processing kind of applications, image manipulating applications. So you can either decide where the complexity should be. The complexity can be either on the encoding end or the decoding end, right? So in terms of the encoding, you can spend all your time and energy to find out the best possible kind of way to make this happen, right? In this particular example, it was fairly trivial. This particular shift kind of worked. But in general, your software has to figure out how much to do. So it can spend all its time trying to figure out what is the best translation from between these images, right? So if it spends a lot of resources up front, right? So the question is, do you want the compression to be more complex? You want the decompression to be more complex, or you want them to be sort of equal, right? Which one do you want? Which one would you want? You have this raw video, and you want to compress them, right? And you're trying to do all kind of techniques to figure out what really happened between these two images, right? So you expect that the difference between these two images are caused by simple stuff like zooming, panning, and all those things, which are translatable, right? None of this will work if they're different scenes. So if you take this scene, and the next one is a scene of the quad, there's nothing similar, so you can't do any of this stuff. But within a single thing, since you're taking 30 frames per second, the changes are not that much if I can do the mathematical formula which figures out what happened, right? What would your goal be in terms of complexity? Do you want the compression to be complicated, or both should be equal, right? What would you want? So think of where you would use this decompression, right? You're using it, say, in a DVD player, right? Do you want the DVD player to be pretty complex, right? Think of how you use it, right? You're using it in your, like, say, YouTube video, right? Do you want the compression to take humongous amount of time? It takes like hours and days to do the stuff, right? But still playable in your device, right? So in general, all these things, they want to push all the complexity into the sending side, but not practically nothing on the receiving side, right? And that's one thing you have to remember. All these things are asynchronous because you want the complexity to be on the compression end, not on the decompression end, because decompression end tends to be your DVD player or whatever. So you don't want all the complexity. And it turns out these algorithms naturally, because of the goal, it does what you want, right? So we'll see how difficult it is to actually find out what changed, because you basically have two scenes, right? If you take any kind of image processing kind of stuff, your goal is you have one image, you have another image. You want to find out what are the things which are similar, what are the things which change, right? And at first blush, the more complex you look, the more globally you look, the better your algorithm would be. You'll see more of the big picture. It also tends to become very computationally intensive, right? And since we're dealing with 30 frames per second, you're going to have 30 of these things next to each other, right? So whatever you're doing, you have to be able to do 30 of these frames per second. And so if you're talking about high definition, so you have 1920 by 1080 in CBCR, 30 of those frames. So you have lots and lots of data to munch on, right? So suppose I do this somehow, and I say what really happened was this ball moved from here to here 2 pixels over, right? On the receiving side, all I have to say is take this image, move those pixels to take this particular block, move it 2 pixels over, you're done, right? So I would have to do a lot of computation to figure out what really happened to this round object from here to here. I had to figure out where it went. I had to see if it went up or down. I had to see if it really translated or what have you. On the receiving end, once I get the instruction, all I have to do is do this simple operation like moving or what have you, right? And as you will see, as you may see from your project, right? The time to compress these things would be in 10 times of real time or what have you. But to play it back, it's fairly simple, right? And you might also notice that if you work on the project, some of the compressors may ask you, do you want to do a single pass or multiple pass, right? Multiple pass is going through the image over and over again, trying to find out the best possible way to do this stuff. And if you do that, if you add that, then it becomes even slower, right? And the more passes you have, the better compression you get, the better quality of the output you get because of the noise which is induced by this process, right? And that's one of the reasons why if you look at the video from your DVD or something, it's usually better than what you do from your home kind of setup, right? Because you have to do it, the more times you do, the more computation you throw at it, you tend to get better output, right? Okay, so in the first sense, we are talking with a macro block based algorithm, right? Which is sort of what we know from the JPEG kind of run. We take the image into these square blocks and we are trying to figure out what's going on, right? So the idea here is we look at two frames. One is a target frame, one is a reference frame, right? And as you will see, this reference frame can be from the future later on. But essentially, we take two frames and we are trying to figure out if I had sent you this frame, how would the next frame be, right? So I want to say for each of these objects in the first frame, what is the difference in the second frame, right? So the idea here is, let's say so let's say in the target I have one of this stuff, right? And in the reference I have this stuff. It kind of shifted, right? I want to take this block, right? And from the reference one, I want to see where it fits in over here, right? So I know it moved, right? I don't know how far it moved. So it's possible that this moved from here to somewhere very far, right? So in that case, you may assume that it's so far that you don't, it's not possible, right? So if you take image in the first, let's say the first frame there's a ball here, and the second one it's over here, right? Like a speeding bullet or something. So it went within the 30th of a second all the way across. So you can think that's not likely, right? You may assume that in likely cases, it's going to be, say, over here. So what we do is we have to choose where it could have moved, right? That's a parameter that you have to choose. And based on where you are, you have to say, I'm going to assume that it could have moved, let's say, certain amount, right? And I'm going to see within that new area if the object matches, right? So I take this particular thing, I sort of look, so I take this square, I take it up here, I try it here, it doesn't, see if it fits, see if it fits, see if it fits, like one across, like this, right? That's a naive approach. That's a brute force approach. It'll work good, but it's horrendously expensive, right? So essentially, for every frame, for every little block, I'm going to take a block, look to see if it's on. I take this block, right? I see if it fits here, fits here, fits here, fits here, fits here. Then move down here, and all those things, and I find the best match for each one of them. So if I do this for each macro block for each frame, and imagine I have to do this for 30 frames per second kind of stuff, right? So the notion is I have to figure out what is the block size I'm going to look at that I'm going to match, right? And we'll see the more complex ones have to look at bigger and bigger blocks, right? If you look at the small block, you may miss the fashion that this is a circle or something, right? So they chose 16 by 16 block for the first case, right? And then you have to figure out what is the area that you're going to look at, right? So what is the area that you want to look at within which you think it would have moved, and then you're trying to figure out what it is, right? The larger the area, the better your algorithm might be, depending on what you're taking, right? So again, this goes to photographic kind of thing. So if your camera is here and you're watching something here, within a 30th of a second, it's likely that it moved enough, right? Whereas if you're shooting something on a mountain, within 30th of a second, it would have hardly moved. Mountains don't move, So you don't know what it is, so you kind of choose a number, and essentially the problem is how do you match this onto that thing, right? And it's, from an algorithm perspective, it's not a super complicated algorithm. From a practical perspective, remember you have to do this for every block of this frame, and you have to do it 30 frames per second. So it tends to be lots and lots of computation, right? And we are out of time, and I'll go through the different mechanisms of doing this stuff. But remember what's the goal and why we're doing this stuff, right? I see you on Wednesday.